Hello, everybody. Thank you for joining us. Feel free to say hi in the chat. As always, if you're new to these streams, let us know where you're coming from. In the meantime, I'm going to kind of set up what we're going to do today. So today is all about generalizing what we've done with a lot of string comparison that we've talked about. So we've introduced substrings before in previous streams, and Hamming distance, and finding a subsequence of certain strings. But we're going to take the next steps here, and the way in which we're going to do that is by applying what we had started to learn a little bit about dynamic programming. And there's a classic example of dynamic programming that we saw, which is where we looked at Fibonacci sequences. So we had a couple different examples of this. We had Fibonacci rabbits, and then the rabbits became mortal. So we had a death condition too, which made things complicated. But the idea is if you can ever find what's called a recurrence relation, or an expression of a function in terms of smaller inputs to that function, and for Fibonacci, that's the nth Fibonacci term is equal to the sum of the n-1th term and the n-2th Fibonacci term. If you can ever find a way of relating a function like that in terms of smaller inputs, a lot of times it leads to an obvious dynamic programming algorithm where we build up subsequently larger and larger values of the function, starting with small values. So we're going to see how to apply that paradigm in the context of comparing strings in a more complicated example than what we saw previously when we were just working with rabbits. But the rabbits prepared us for what we're going to do. There are two big ideas, I should say, that I think we're going to encounter. And I have a few slides for what we're going to talk about at certain points today, just to kind of give us a highlight visual of what we're doing, because this is what we're going to see. Understanding what we're doing conceptually and being able to see it is really going to be vital to helping us understand exactly how the algorithm is going to work. And so there are two big ideas along those lines that we're going to cover. The first idea is that if we look at an alignment of strings, what do we mean by an alignment? Well, if we have these two strings, ATG, TTATA, and ATCG, TCC, we would like to slide the symbols around in these strings so that we can see where are the positions that correspond to places where there's similarity, where are there regions in this alignment of the strings that correspond to differences. And so if you have any background in bioinformatics, this kind of thing is going to be very familiar and very comfortable to see. The question is, how is it that we can take an algorithm that takes these two strings as input and then produces a good alignment of the strings? A lot of biologists probably take this for granted, but we're going to see how to solve this problem of finding the best alignment of two strings. And now an important point here is, what constitutes the best alignment? That is going to be something that we work on not just today, but in future streams as well. So this stream is called Alignment Episode 1, and we're going to see that we're going to need multiple parts of this because dynamic programming is going to appear in a lot of different contexts, not just sequence alignment in biology. And that's cool, but even within the context of sequence alignment, what we're going to see is we can constantly change it, update it, make what we're doing a little bit more sophisticated. And with comparing strings, it's always going to be right there behind the scenes. So that's big idea one that we're going to have here, is that I can think about alignment of sequences, and this is as much a conceptualization for us, a visual for humans, as it is anything else. We can take this alignment of strings, and this alignment of strings corresponds to a network path. So if you note, probably one important thing to note, you look at our network, the number of rows is always one row extra compared to the number of symbols. So each symbol corresponds to a position between columns of this network. So string 1 is represented here on the rows. String 2 is represented over here on the columns. And if you think, well, how does this network, this particular path through the network, correspond to this alignment? If we take one symbol from each of the strings and line them up, then we're looking at diagonal edges. And notice I colored these two edges red to indicate that they're matches. So the T here matches against the T there. If instead, when we look at our alignment, we have an insertion or a deletion, we commonly use the term indel to refer to insertions or deletions, meaning places in the alignment where you have a gap symbol to indicate, well, you see the symbol in this string, but not this one, or you see the symbol at this position of this string, but not this one. When we move through the network, we're going to be going either horizontally. So in this particular case, I'm using the C from the second string, but I'm not using any symbol from this string over here, so I'm going to move horizontally. Notice I have two more diagonal edges here. I now can go vertically. So when I move vertically, that corresponds to using a symbol of the first string, but not the second string. And now note, I'm using a symbol from each string, so I'm moving diagonally, but we use this color purple to indicate that there's a mismatch there. And then we move down one more symbol and then one more mismatch. So there are four types of edges. Horizontal are blue, indicating using one symbol from the top string. The vertical ones are green, corresponding to one symbol from the string that indexes the rows. And then your diagonal edges mean take a symbol and align them from both of the strings, but sometimes it's a match, which is red, and sometimes it's a mismatch, which is purple. That's big idea one. The point is, if you give me any path, I can produce any alignment. So there is a one-to-one correspondence. If you look at this path, I could easily have reproduced the alignment from it. And any alignment corresponds to some path. So I could change the alignment of these two strings. The strings have not changed, which means that the network itself is the same, but the path that is highlighted through that network is different. And this path you can see over here now corresponds to a different alignment of these two strings. So we have A and T against gap symbols, and then G against an A as a mismatch, and then T against a T as a match, and so on. You'll notice that what we always have to preserve is the order of the symbols encountered in the top string needs to be this ordering of symbols here, and the ordering of symbols in the bottom string has to be this ordering of symbols here, but we're able to insert these additional gap symbol hyphen symbols at certain places to allow the symbols to slide around a bit and to allow us to find more similarity in these strings. We're going to use this quite a bit. But the question becomes, how do we use that? Why is this conceptualization useful? Well, what we're going to do is we're going to weight the edges of this network, and we're going to change the problem of saying what constitutes a good alignment as, well, what's the alignment having the best score? Now we're moving into the realm of a computational problem where I'm going to say, let's optimize over all possible alignments of two strings. Which one is better? Is it this one or is it the one we saw before? You might have a preference for one of these versus the other. I would say, I think I would prefer the first one, but we should place this on firmer footing. So we shouldn't just say, well, we're going to look at the alignment that we produce. The point of adding computation to any discipline is to rigorously assess what makes one versus another better. And so we can change what that definition is of better, and that's going to produce slightly different results for us. That's part of why what we're going to do here is going to take more than one stream to discuss. The other point is that if I'm looking for the best scoring alignment, well, the framework here that I'm applying of saying, let's find the longest, or finding not just an alignment, but a path in the network, is to say, how can I take the score of that alignment and somehow frame it as the score of this path? And what I will do is I'm going to weight the edges of this network, and then I'm going to be looking for the best scoring path from the top left to the bottom right. If the score of that path is the score of the alignment, and I'm looking for the best scoring alignment, then it's just a matter of finding the best scoring path. And the reason why I want to weight these edges of the network is that we know how to find the longest path in a network like this. Our second big idea is that dynamic programming is really helpful for finding the longest path in a network, as long as the network doesn't have cycles in it. I'm going to imagine that instead of each node having 3 incoming edges, like we have in that alignment network, imagine that you have a network that just has 2 incoming edges. We can get a recurrence relation for the best scoring path, the path of maximum weight, that ends at this particular node by saying, well, it can only have come from one of 2 places. The best path into this node must have come from either the node above me or the node to the left of me. If I come from the left, then the score at my node would be the score at this node plus the weight of this edge. If I came from this node, well, the score here would say it's got to be the best score into this ending at this node plus the weight of this edge. So that's a powerful idea because it says consider both of those 2 things, the score at this node plus the weight, the score at this node plus the weight, and simply take the maximum of the 2. The best path that ends at this node must be the better of those 2 options. I'll show you a quick example of how I take that recurrence relation, saying take the maximum of the length or the score ending at the node above me plus the weight of the edge coming down vertically, and take that compared against the score at the node to the left of me plus the edge coming in from the left. So I can apply that recurrence relation repeatedly. The first node I could look at is this node. The key point is I want to make sure that I consult a node where I know the 2 predecessors. If I look at a node here, I have no idea what the score of these 2 nodes is, so it's pointless to consider this. But if I look at this particular node, well, I'm going to say, what does the recurrence relation say? It says the score of a best path, the maximum weight path that ends at this node, has to be one of 2 things. The score ending at this node plus the weight 0, or the score ending at this node of 1 plus the weight 3. And we can see, well, which is better? It would be better to take 1 plus 3 than it would to take 3 plus 0. And so I can assign that node a value of 4. In this way, I can move down. Maybe I could go column by column. I also could go row by row. I am now able to set either this value or this value. Let's set this value, and I'm going to say, what's bigger, 4 plus 6 or 5 plus 0? Well, it's 10. And so this value becomes 10. Similarly, 10 plus 4 is bigger than 9 plus 3, so this becomes 14. And 14 plus 6 is bigger than 14 plus 1, so that last value becomes 20. Now it's just a matter of applying my recurrence relation over and over, column by column, and eventually getting a value of 34. What's nice about that particular value is that that is now the length of the best path in this network. So we started with a network, and I set all of the values across this initial row and initial column because there's only one path in. So 0 plus 3 is 3, plus 2 is 5, plus 4 is 9, plus 0 is 9. Same thing down this initial column. But after I apply my recurrence relation, just working column by column, whatever the value that I have here is the length of a longest path in my network. So it might not be immediately clear what that length was if I just gave you this network and said you have to find the best path. There's actually a huge number of options to go from the top left to the bottom right. And you might not know, am I 100% sure that I found the right answer? But in this case, dynamic programming gives us a 100% crystal clear number with verification that I'm certain that the best path that ends at this node, starting here, which is what I'm looking for, has score equal to 34. Now, the alignment network doesn't yet have weights assigned to it. So if we look back at our idea number 1, which is that every alignment corresponds to a path in a network, I don't have edge weights. That's the one thing that's missing. If I could assign edge weights, then I could solve the same type of problem and say, well, what's the best path that starts here and ends here? And if the score of this path is the score of my alignment, great. I find the best path from top left to bottom right. And then that tells me what the score of my best alignment is. And if I figure out what that path is, I can use that path to infer what this alignment is. That's the subject of what we're going to get into today. We're going to apply those ideas repeatedly. And we're going to kind of build up our understanding and our sophistication for applying this, starting with basically the simplest type of question that we could ask about two strings and using this alignment path formulation to find the best path in a network. What we will see is as the problems get more sophisticated, the edge weights are going to change and the network itself eventually is going to change, but that's enough for the setup for now. I should point out, of course, if you're interested in more of this particular type of thing, well, we have, in my biased opinion, is the best treatment of this in the world in our bioinformatics algorithms project. So you can check that out. And you can also check out our Great Ideas in Computational Biology course, where we're going to be getting more into the theoretical side of this and understanding how these beautiful algorithms work. Today is going to be all about code, of course. So we're going to see all this on the coding side. But I think we're essentially ready to get started. So as always, please make sure you like and subscribe. It helps keep us visible. And then we have a bunch of stuff in our video description. So make sure to join our mailing list and our Discord to find out about upcoming projects and courses that we're launching. We even have projects and an ebook for Philomath members, and there's starter code and completed code for everything that I do here. So all of that is in our video description, and please feel free to check it out. In the meantime, let's code. Krish, good to have you here. Sarah, welcome. Rodney, hello. We're going to look at LCSQ first today. All right. As always, let me know if you have any questions. If anything's confusing, we can handle it as we go. Usually we'll take a look between problems. In LCSQ, we're going to look at the problem of finding a longest common subsequence of two strings. In previous problems that we've looked at, we considered substrings, and then we introduced this idea of subsequences, meaning a collection of symbols that occurs in a string in order, but that's not necessarily contiguous like a substring. So every substring is a subsequence, but not every subsequence is a substring. And subsequence is an important concept in computational biology because, well, you might imagine that you have some region of similarity, but then a mutation inserts a symbol within one of these strings, and we don't want any approach that's based off of substrings to fail and not be able to find, well, yes, there were a few places where symbols got added or subtracted, but we're still able to identify that this is a region that largely exhibits a great deal of similarity. So this problem says, if we're interested in similarity, and we know that these types of mutations happen a lot in biology, why don't we try to find the subsequence of two strings that's as long as possible? So, in other words, our input is going to be two strings, and our output is going to be a longest subsequence that is common to both S and T, meaning one that occurs in both of these strings. And the autograder here is going to allow us to return any one of those. So if there are multiple ones, then we're going to say return any one. At first glance, of course, this problem doesn't have any clear connection at all, probably, to this idea of finding a longest path in a network. It seems like a pure string problem and something that probably doesn't have a great deal of connection to sequence alignment. But that's not true. And there's a critical insight that we have, which is that if we look at the matches in an alignment, they're going to correspond to a common subsequence of two strings. So if we were to imagine that we trace a path in our network from top left to bottom right, as we go, any red edge that we encounter is going to correspond to a symbol that's shared between the two strings. If these were substrings, what we would be looking for is consecutive red diagonal edges. But these are subsequences, so it's okay, for example, if I were going to say A and T are shared between the two strings, but I skip over here, and then I say, oh, well, I also see a G and a T that's shared between the two strings. So I've missed out a letter, in other words, in this string. Actually, ATGT is a substring of this string, but it's not a substring up here. So if I'm finding a longest common subsequence, what I'm looking for is, in essence, an alignment or a path through this network that uses as many red edges as I possibly can use. And if that's the case, what I'm really looking for is the path from top left to bottom right in this network that encounters all of as many red edges as it can, meaning if I weight those red edges 1 and all of the other edges equal to 0, and then I find a path of maximum weight in the network, I will have found a solution to my problem. So by the symbol matching problem, what I mean here is accumulate as many matches as you possibly can in the alignment of these two strings, but all those matches are going to correspond to a common subsequence that's as long as possible in the two strings. So two problems here that seem kind of unrelated actually are inherently very related, which means here is a string problem of finding longest common subsequence, but actually we can solve it a little indirectly by solving the problem of finding a longest path in this network from top left to bottom right, where only these red edges get weights of 1 and everybody else gets a weight of 0. In order to solve that problem, what we need to do is apply our dynamic programming formulation to it. So we need a recurrence relation. Once we have a recurrence relation, this problem will be a little bit straightforward to solve. And in this case, our recurrence is going to have a little bit more complexity than what we saw with our introductory longest path problem where everything was rectangular. Every node has 3 incoming edges to it. And there are also 2 different cases. So most of the edges have weight 0. Every horizontal edge, every vertical edge will have weight 0. The diagonal edges are going to have weights equal to 1 or 0. And the reason why that's the case is sometimes when we look at our network, we're going to have a mismatch, or purple edge. Sometimes we're going to have a match. And matches are going to accumulate a score of 1. Mismatches are not going to accumulate anything because we want to keep track of as many matched symbols as we possibly can on this journey from the top left to the bottom right. However, the idea of the recurrence is the same. I'm finding a longest path. I have 3 predecessor nodes. The score of the best path that ends at my current node, which I'm going to call length of ij, is the maximum of, well, what was the best score ending here? What was the best score ending here? And what was the best score ending here? In each case, I also need to add the edge weights. In case 1, where you have a mismatch, you're adding 0 each time. So I'm really just taking the max of these 3 scores. In case 2, where this corresponds to a match, I'm taking the max of these 3 scores, but I'm adding 1 to whatever the length of I minus 1, j minus 1 is. Once I've got that idea, I could then use it to fill in a sample table. So here is our network corresponding to aligning the strings ATGT, TATA, and ATCG, TCC. So we have a string on the left and a string on the right. Now, we're going to start off by setting all of our top row values equal to 0. There's no way I'm going to be able to pick up any matches. And all of these elements are going to be 0. All of these elements also are going to be 0, because the only possibility is to just go down this first column, and the weights of all these edges are 0. So you get the first row and column for free. We're going to use that here momentarily when we implement this. And then we're simply going to go row by row. So as I go row by row, this element will be 0. This element is 1 because I'm taking the max of these 3 elements, but I have a match edge here, so I'm going to get to set this value equal to 1 because this gets a weight of 1. Now when I look at this node, I have just the max of these 3 things, but now that this value is equal to 1, it makes this value equal to 1, and it turns out that logic applies all the way across. When I go one more row down, this value here becomes a 0, of course. This is 1 because it's the max of its 3 predecessors, so it takes the 1 from above. This value is a 2 because it takes the max of all these 3 ones, but it gets a bonus value of 1 from this red edge, and so forth. So this becomes a 2, that 2 kind of pushes over to the right. This 2 here could come from one of 2 places. It can't come from above, but it could come from a 2 plus a 0 or a 1 plus a 1, and then we carry on. In this way, you can proceed row by row, filling in all of the values by considering your 3 predecessors up, left, and diagonal, adding 1 to the diagonal value if you see that you're at a match. So again, for example, here, this becomes a 3 even though the predecessors are all 2. And the reason why is because we get this bonus extra plus 1 value corresponding to the weight of a red edge. And at the end of this process, after we go row by row, we wind up with a value of 4 in our bottom right node. What that value of 4 tells me is that I know that the length of a longest common subsequence is equal to 4. And you can see it here. We had this before. We thought, well, ATGT and ATGT, you can kind of see that that appears to be a longest common subsequence of the 2 strings. Of course, if I gave you 2 strings of length 20,000, you're going to have a much harder time visually inspecting these strings to try and find similarities, but the algorithm is not going to mind. So at the end of the day, the algorithm will still make the network, apply the recurrence relation, and say, what's the value that I see in that bottom right element? That's going to be the length of a longest common subsequence. This is the beauty of nice algorithmic design and provably optimal solutions with dynamic programming, that at the end of the day, I just need to apply my recurrence relation and access whatever that value is. There's a natural question too, which is to say, well, that's not actually what I'm trying to solve. I'm not interested in the length of a longest common subsequence. What the problem is asking me to do is to produce the longest common subsequence itself. And that's a good point. But the first thing that I want to be able to do is solve this initial question of finding the length of a longest common subsequence. As we're going to see, it's going to be very useful for solving the problem that is desired. And to that end, what I'm going to do is I want to build this scoring table. So I want to I'm not going to explicitly make the network, But what I am going to do is I will explicitly make the scoring table that I'm working with, noting that the number of rows that I have is always one more than the length of this string, and the number of columns that I have is always one element more than the length of W. So here the length of W, for example, is 7. It has 7 symbols, but we can also see that there are always 8 columns in our table. So I need to make a table where the number of rows is equal to the length of V plus 1, the number of columns is equal to the length of W plus 1, and where I simply proceed through that table, applying the recurrence relation at every position, and then what I'm interested in is the value in the bottom right. As we transition towards code, the function that I want to write is going to be called LCS score matrix. And the idea of this function is to take 2 strings, and now you'll note this function is also going to specify that it could take a list. That will become clear after we solve this problem. But this indicates in our type hints that we have a list or a string as input. In this particular case, we're going to be working with strings. And at the end of the day, we're going to produce a 2-dimensional list of integers corresponding to our scoring matrix for longest common subsequence. We're ready to show how this function is going to work. And in this particular case, this function first should make the table. And we'll do that because, well, when we make the table, it's going to allow us to know, the first thing we want to do is make sure that the table has the right dimensions. I made sure to point out that we know that the number of rows is equal to the length of S plus 1, and the number of columns in this table is equal to the length of T plus 1. If I don't know that, there's no way I can solve the problem. So it is a good practice to write down what these temporary variables are, and then that allows us to create the table, although the table is going to just start off as empty, but I'm going to make all of the values in it. So I'm going to call this table DP to stand for dynamic programming. And it is going to be a 2-dimensional list of integers. It can start off as empty. Let's give it some default values. So all the values are going to start off as 0 by default. And I can do that by ranging over the number of rows. And once I range over the number of rows, then it's just a matter of saying, well, the current row is equal to an empty list. And in fact, I could say it's a list of integers. We can be very precise. And once I've established that as a list of integers, then I can say, all right, let's range over the number of columns that I have. And for each column index that I see, I want to append a 0 to it. And then at the end of this process, I'm going to append my row to it. The other way, of course, I could do this is to say, well, the row is just a bunch of zeros times the number of columns that I have. So that will make that a little bit tighter. There are some values that we've already set that we know are correct. So the initial row and column are already correct. When we looked at our example, this first row and column of our scoring table is always just going to be a collection of zeros because there's no way I can pick up a match if I'm ranging across the top row or the left column. If that's the case and I know they're already right, then what I need to do is we're going to range over the interior of the table and apply the recurrence. So what I'll say is, if I want to range over the interior of the table, I don't need to consider row 0, and I don't need to consider column 0. So we know how to range over all the values of a table. We can do that with a 2-dimensional or nested range. But I want to make sure that I specify that the row index is going to range from 1 to the number of rows, and the column index is going to range from 1 to the number of columns. And as I go through that, what I want to say is apply the recurrence. And to apply the recurrence, we need to consult the three predecessors, meaning what's the value above me, what's the value to the left of me, and what's the value that comes diagonally above and from the left. So I'll say the up value is equal to, let's consult my table. And if I'm looking one element up, then I'm looking one row previous, but I'm in the same column. If I'm looking left, I'm in the same row, but I'm looking one column previous. So we look at column -1, but we keep the row index the same. And the diagonal value would say I'm one row previous, but I'm one column previous too. So I'm going left and up. And if that's the case, then I'm setting my indices to row -1 and column -1. Of course, remember, it would be nice if we said, oh, dp of row col is equal to the max of the up, the left, and the diagonal values. However, there's a case that we have to consider. So remember that the diagonal value may include an edge of weight 1. And when does this occur? Well, this occurs when the corresponding symbols of the strings match. So I need to have a check for when this is going to occur. And the indexing of this check is going to be very important. It needs to be S of something equal to T of something. And if that's the case, then I have a match. And I'm going to say, well, in this particular case, I'm setting the table value of row col equal to the max of up, left, and diagonal +1, because I need to include my edge weight. I still want to have this test, but now this is going to be an else. And this is the case where the symbols don't match. So this is a match. And this particular case is a mismatch. After I do this, of course, I want to make sure I return my table. But the only thing that is left to do is to make sure that I have the indexing correct. And here is where it would behoove us to write out an example short collection of strings, maybe of length 3 and 4, make the table ourselves, and then identify, well, what's the pattern that we see? Probably an easier way to explain this without going through the process of doing that is to say, well, if I'm at row 1, column 1, what symbols am I looking at? Well, they're the first symbols corresponding to S and T. So if that's the case, and we look back at our picture, right? If I'm setting that value, well, I'm interested in the initial symbol of the two strings. So if I'm at this value, for example, I'm interested in, this would be row and col are equal to 2, but I'm interested in the symbols at indices 1 and 1. So the pattern then is that I'm always looking, if I'm working in a zero-based indexing language like Python, I'm always looking at whatever the previous index was. Actually, that'll apply even if we're not zero-based. So I make that check. And in this particular case, remember the rows index S, that's our first string. The columns index T, that's our second string. And so I just need an index that's one previous. If those two symbols are equal, well, I can do that with a quick equality check. And so I have a match, and I'm not going to need to add 1 to my diagonal value. So our function is written. Everything is in good shape. There's just one kind of major issue, which is that the problem doesn't ask us to produce the scoring table. What the problem asks us to do is to form a longest common subsequence of two strings. So we need a function that's going to do that. I would imagine that this scoring table would presumably be very helpful. So I'm going to go ahead and write the very start of this function, which is to say, well, if the length of the either input string is equal to 0, then what I want to do is return an empty string. If I have an empty length string as input, it can't possibly share a subsequence with anything. So I'm going to have a quick check of that. I don't need an error message. It's fine to input a string of length 0. And then I'm going to define my score matrix of the two strings. But then the question is, what do we do now? It might be that making that scoring matrix doesn't actually help me reproduce an LCS, in which case we're not going to be able to solve the problem. The fortunate thing is that once we have the table, we're going to be able to form the LCS by remembering and reproducing the edges that we encountered. In other words, if I'm able to figure out somehow what the best path itself is from here to here, all I need to do is identify the match edges that I encounter along the way. So once I know that this value is 4, I'm just looking for any path that has 4 match edges from the top left to the bottom right. There's 2 ways of doing that. The first approach would be to try to do it greedily. I could start in the top left and then try to form as many edges as I can to make sure that I get a count of 4. The problem with that is if I give you a huge network corresponding to 2 very long strings, it's not clear at all which direction to go, and so there's a good chance you're simply not going to reconstruct an LCS of length equal to whatever the maximum is. Fortunately, there's a rigorous way of doing this, which is if I remember where I came from, and so here is the table. If I have a value of 4 there, I could have come from any of these 3 directions because this is a mismatch edge, so there was a big tie. So let's say I came from this direction, and when I'm here, there's a tie again. I could have come from here. So there's nothing special about what I'm picking. But what I'm showing is at every point of the scoring table, I could simply ask, which value did I come from? Which value caused me to set a 4 here? Again, I have a tie. I could have come from any of those directions. Let's say we pick the diagonal direction. There's nothing special about it because we know there is some path ending here that has a score equal to 4. That's good. That means I'm going to be able to find 4 matches somehow as I go backward. In this particular case, I don't have a choice. So when I look at this particular node, this node has 3 predecessors. The diagonal edge is a mismatch, so I'm simply taking the max of 3, 3, and 4 to produce this 4. In other words, the best path must have come from this node. So I no longer have a choice. I must have come from the up node. When I reach here, I actually do have a choice. I could have come from here, or I could have come from here, but I can't have come from the left. And the reason why I could have come diagonally upward is because this match edge gets a weight of 1. So when I consult these 2 values, we have a 3 plus a 1, or a 4 plus a 0. Either one gives me a value of 4. I could pick either one. I'll pick the one that corresponds to the diagonal. Now I have only one choice. I'm at a mismatch edge. I must have come from this value to give me a 3. I must have come from this value because these up and left values are 2. So 2 plus 1 is going to produce the maximum. Here I must have come from the left. And then once I reach here, I must have come diagonally. And I must have come down diagonally from here as well. And if I highlight those edges, what do those edges correspond to? Well, all I have to do is look at the corresponding symbols that I see. And those symbols are an A, a T, a G, and a T. So if we look at our original case, the edges that we have are this edge, this edge, this edge, and this edge. And you can see A, T, G, and T. So that gives us, as we work backward, our longest common subsequence. Pretty good. So to make this longest common subsequence, the only thing I have to do is work my way backward through the table, figuring out at any point in time which direction did I come from. And I could have also stored this when I made the table, but as I'm going to show you, there was no real reason to do this because I can always just look at the table and say which of these three values is the biggest. Keeping in mind, sometimes I have to consult a match edge as well. And as I go backward, every time I encounter a match, I'm simply going to append it to a string that I'm making. So we can take that idea and put it into code. So if we're looking at finding the longest common subsequence, I've made my scoring table. I need some way of knowing where I am. So I will use indices R and C to store where I'm looking in the table. And R is going to start off as the length of S, because remember, the number of rows is the length of S plus 1. So the elements of the row index will range between 0 and length of S. So row indices range from 0 to length of S. And our column for the bottom right element is going to be the length of T. So the column indices are going to range from 0 to the length of T. Once I've set those two values, I will continue updating them. So I'm going to remember where I'm coming from. And to do that, the first thing I'm going to do is I'm going to say, let's establish what our result is going to be. So this is our answer. So eventually what we're going to do, and I'm going to store this as a list of strings for the same reason that we've done this previously, which is that in a lot of languages, Python included, if I were to set this equal to a string, I'm going to have a bunch of string concatenations. All those string concatenations are going to be potentially memory intensive. And so instead I'm going to make a list of strings, and then at the end, I'm going to join all those strings together with this join function that takes result as an input. So this concatenates the symbols we find into a string. Once I've done that, then I just need to keep track of how long am I going to run this algorithm. I'm going to continue moving backward. So we are going to move backward in the table for as long as we're in the interior. Because once I hit the first row or the first column, there's no way that I can get additional matches. So once I hit initial row and column, I am done. So we're going to have a while loop that says while it's the case that I'm in the interior, and I can check that I'm in the interior if R is non-zero and C is non-zero. So if those two things are true, I know I'm in the interior. We've seen that same sort of thinking here, right? So we ranged over the elements starting at 1 in each case. So the indices I care about are going to be making sure that R is non-zero and C is non-zero. And then as I'm looking at this, I'm going to say, which value did I come from? Yeah. If it's the case that when I look at the dynamic programming table that I made, the scoring table, if the current value is equal to the value that happens when I look one column previously, well, in this particular case, I came from the left and I didn't get a match, but what I want to make sure that I do is that I update my row element. So, excuse me, C minus equal to 1. Right. So this says move one element to the left. Else if, when I look at dp of RC, if that current table value is equal to the value above me, meaning dp of R minus 1 C, well, I came from above. when I set that value, and I want to say r minus equal to 1. Else, well, we could be very precise, you know, separating out cases and making a check that the table is valid, meaning it doesn't have any weird values in it, and you know, it's not the case, for example, that the current value is equal to 3 more than whatever the diagonal value is. That's probably a good thing to do. I'm not going to make that check because I'm going to assume that we produced a good scoring table and we're working with these Rosalind problems where we're not extending it to every possible circumstance we could work with. And so in this particular case, I'm going to say, you know, let's ensure that we're going to move up 1 row and up 1 column. So I'm moving diagonally. But before I do that, I want to say there's an important question that I should ask, which is, is the current diagonal edge a match edge? Okay. And so if that's the case, well, I should say, you know, if it's the case that S of R minus 1 is equal to T of C minus 1, here we get to make our check again. So in that particular case, I know I'm at a match. And if I know I'm at a match, then I want to append the current symbol to my growing list that I called result. Now notice this is equal to this, so I could have said or append the corresponding value of t. It turns out they're both equal. Once I've done that, I'm then going to move up 1 row and over 1 column. So I could try this on a sample input. If we look at our main, we have our little stub that allows us to find an LCS of 2 strings. So when I bring up a terminal, I'm going to make sure I've saved my code. This is LCSQ.py, and I can run it. And I see that I get the string GTTCAA. If I look at the platform, it has the right length equal to 6. It's not exactly what we see in the sample output. And the reason why is, even though it has the right length, the problem is that as I went backward, I kept appending to the right side of the list. And the issue with that is, because I was moving backward, my string is going to be backward. If I look at the 2 strings that I have that are input to the function, GTTCAA is a shared subsequence. But the problem is it's in the opposite order. So if we're moving backward, we can see GT, and then another T, and then CAA. And we can see GT, and then another T, and then CA, and then another A. So everything is good, I think, but the problem is that the LCS is, unfortunately, reversed. Fortunately, so at this point in time, our LCS has been found, but it's backwards. And fortunately, Python will give us a function to reverse a given list, which is just result.reverse. So now when I call that, it will flip my string around that I found to say AACTTG. Once I've done that, I can see that that appears to be another valid solution. I can download a data set and run this on a larger data set. So I need to make sure that I put my data set there. I've already got a data set. Oh no. Okay. And now I'm going to comment out my parsing code. And once I comment out my parsing code and I rerun, I should see something in the output. And let's see if we get it right. And we do. Success. And this is a correct solution, even though we didn't get the exact same solution that we got on the sample output. You might notice, I'll make a very brief point. You might switch the order of these, and it's possible that you're going to get a different result. So, in this particular case, I'm going to prefer coming from above early on instead of coming from the left. And when we run this, you could go in and look at the output, but the LCS that you're going to obtain is going to be slightly different from the one that you obtain here. So one thing you might do is see how that affects the output that you get. And you could go through and identify where the positions, where the strings are actually going to differ. Do they start off the same here, TCAC, GTAC? No, they don't. So we wind up with a different LCS. That comes from just changing the order in which we consider these if statements. There's a deep point to be made here about bias in algorithms, that something as simple as the order in which you consider an if versus an else if can actually produce different end result behavior in the object that you produce as a result of your algorithm. But in this particular case, all we're looking for is one LCS. It doesn't have to have any special properties, and we can consider the problem solved. If you have any questions, let me know. I'll set up for the next question. YP, you had a question about, shouldn't it be otherwise? What's the it in that sentence? We're going to look at LGIS next, by the way. If we added to the column, but R is the same. Okay. So what this check is saying is the current value equal to the value above me, meaning one row previous? So we think about the rows going this way and the columns indexing that way. If I came from above, then I know that I need to go up one. So the row index is going to be subtracted by 1. If when I look to the left, meaning I look one column over to the left, and those values are equal, then in that particular case, I need to say, let's subtract 1 from the column. And in the diagonal case, I'm going to do both. Yeah, no problem. I would make that mistake if I just sat down and said you can't say anything, you just have to type out the code here. I'd probably make that mistake 10% of the time. In fact, I think I mixed up and left when I said it, but that's the benefit of always talking to yourself. And if you need a rubber duck or whatever, that can be helpful too. But I usually don't need a duck toy to talk to myself. I enjoy it anyway. All right. LGIS is up next. So LGIS. We're looking at LGIS on longest increasing subsequence, which is frankly not the most biological problem. There's a little bit of a biological setup here, which is that genes on chromosomes often wind up scrambled in different orders. And one of the things that the problem doesn't tell you is if you're looking at organisms like ourselves with multiple chromosomes and you compare us against a related organism like a mouse, the genes wind up flying around from one chromosome to another. And this particular problem is not modeling that. It's looking at, well, imagine you have two chromosomes that have a collection of genes on them, and those genes are shared, but we see that the orders of those are different. There's a very simple measure of similarity that you might apply, which is to say, well, let's take the genes in one of those chromosomes, and we're going to number them 1 to n in order. And then we're going to say, what's the occurrence of each of these genes in the other chromosome? And then what's the order that they occur? So maybe gene 3 occurs first, actually. In this particular case, let's say we've ordered them in one chromosome, and now in the other chromosome, the order in which these genes appear is 5, 1, 4, 2, 3. So a very simple measure of similarity would be, after you've numbered the genes 1 to n in one chromosome, identify the order of the genes in the other chromosome that are like maximally shared. And what that means in this case is I'm going to have an input n, which is redundant, and I'm also going to have a permutation, an ordering of the integers from 1 to n. And what I would like to find is, if I'm comparing this against 1, 2, 3, 4, 5, what's the shared sequence of increasing symbols that's as long as possible? In this case, it's 1, 2, and 3. And I'm going to also ask the question, what if we go in the opposite order? So there's no biological meaning there, but if we went in the opposite order, we would be looking for 5, and then 4, and then 2. It's a very mathy question. But the insight to it is that, well, what we're actually doing with this question is we are finding an LCS of two things: the given sequence and the order 1 to n. So if I'm given again 5, 1, 4, 2, 3, what I'm really looking for is a longest common subsequence of this thing and 1, 2, 3, 4, 5. If I solve that problem, it's going to tell me that the answer is 1, and then 2, and then 3, because that's a subsequence of the two strings that's as long as possible. The order is fixed because, well, I'm finding a common subsequence against 1, 2, 3, 4, 5. And that means if I want to solve longest decreasing subsequence, our insight there is going to be very similar. Our insight there is that we're finding an LCS of the given sequence and n to 1. So there's a very quick way of solving each of these questions, which is, let's sort the sequence. Fortunately, Python gives us a way of producing a new sequence that I'm going to call sorted seq, equal to the result of calling the sorted function on the input. So this gives us 1 to n. And once I've done that, what I would like to do is return an LCS of sorts of the sequence and the sorted sequence. And that's it. The entire problem is finished. The only issue is that LCS returns a string, but I'm going to ignore that for now. And because what I want to do is I want to have this function be the exact same, but I want to reverse it. So I want to say sorted seq.reverse. And now this is what we want, which is this permutation n to 1. And then I want to return the LCS of the seq and the sorted seq. And it is just that easy. The problem is I'm getting a strong suggestion here to say, what is LCS? And I haven't imported it. And in this particular case, I need a function that's very similar to what we've already written, but is not quite what we've done before. Fortunately, I'm going to go to LCSQ, which we looked at previously. And in our starter code, we have another function that we didn't look at previously called LCS sequence. So this is going to take a list or a string as input. What we're going to do is generalize the idea that we had in LCS to take either a string or a list as input and to produce not a string, but in this particular case, what we're looking for is a list. Because when we solve our problem and I want to return 1, 2, 3, well, I want to return that not as a string, but as a sequence of integers. So I need a list to be returned in that particular case. So in some sense, this is generalizing what we had before. If I pass 2 strings into the function, it's just going to give me a list of symbols corresponding to the longest common subsequence of the 2 strings. And so now I'm going to be able to pass in a list. I can pass in a string. It doesn't matter. I'm going to do something a little bit dangerous, which is just to copy all of our previous code. And then I'll go through it and say, how is it that this code is going to change? It turns out the answer is not very much. There are only a few small examples here. First off, if the 2 input things that I have, if either one of them is empty, well, I don't want to return an empty string. I want to return an empty list. That's change 1. But I'm still going to form the scoring matrix. R and C are still going to be the length of the things. It just could be the length of the list, could be the length of the string. When I look at the result, I'm not interested in a list of strings. I'm just going to have an arbitrary list as an empty list. I still want to move backward as I go through this. And as I move backward through this, well, I want to say, which value did I come from? If I came from above, I make this check because I'm just checking the scoring table. Same thing here if I came from the left. And if I come from a diagonal edge, well, I still want to check, the corresponding elements match. In this particular problem that we're going to apply this to, I'm checking if integers match, but that's still a check that's completely the same. And I'm still going to append to this the current element that matches. And I'll make sure I update r minus equal to 1 and c minus equal to 1. At the end of that, the LCS has been found, but it's backwards. And the only thing to do then is not to return the join with concatenating the symbols, but to return the result. So it's never a good idea to duplicate code. But what I'm getting at here is this function would replace the function that we wrote for LCS. And so we wouldn't actually need it anymore. I would just need to, if I were going to solve the problem again, I would need to call LCS sequence of S and T and then print the join of, using an empty string, the join of that result, because the result is going to be a list. So at the end of the day, this is going to be a superior function because it's more general. And otherwise, everything else here is going to be the same. So that's nice. I just need to make sure that I remember to import LCS sequence. So I will say from LCSQ import LCS sequence. And now when I call this function, I'm calling LCS sequence here. And I'm going to call LCS sequence in the longest decreasing subsequence function that I wrote. And now our code should be done. So we'll see how it does on our sample. I'm going to run Python 3 LGIS.py. And notice that we print 1, 2, 3 and 5, 4, 2. That looks pretty good. So let's try to generalize this, go up a level and get a sample data set that is larger. I'll go into LGIS. I'm going to comment out all of my parsing code. Run it again. It's going to take us a little bit of time. And now our solution for this data set should be an output.txt. It looks good. We have increasing values here. We have decreasing values there. 2-line function. So I've copied all that in. I'll submit. And we solved the problem really with like 6 lines of code. So the point of that problem really is to get you to see that even though this seems like a very different problem, it seems like it's tangentially connected to biology, but it's a very mathematical problem in spirit. This paradigm that we've introduced of using our network thinking to get a recurrence relation and using dynamic programming to produce this longest path, which in this case was the longest common subsequence, is extendable to another circumstance. Let me know if you have any questions. We're going to look at edit next. That's our next question to look at. It's interesting to me that more people have solved this question than this question, because if you solve this one, I think it kind of motivates you to solve this one. And if you got this one, maybe you realize that this is solvable too. I don't know. They seem like they're equivalent difficulty. Then edit distance drops off to 2,000. I don't actually want to see who the people are. This drops off to 2,000. And I think there'd be a lot more solutions if they realized all these questions are about of equal difficulty. You just need to have the right framework of thinking about it. Okay. We're going to look at edit, EDIT, which is the edit distance question. We've worked with Hamming distance previously, which is just to line up 2 strings of equal length, count up their number of mismatches. That's a little bit of an introductory approach, frankly, for comparing strings. As soon as one string has different length than another, it's going to fall apart. And in biology, what we have is even similar genes are going to accumulate lots of mutations. They'll wind up with slightly different lengths, even if they're very similar. And we need an approach that's going to allow us to find where those mutations are. We've made a transition towards thinking about alignments, and we've solved this longest common subsequence problem, which maximized the number of matches that we see in an alignment of 2 strings. This problem seems like something that's very different from that, because the input that we have is 2 strings. We're going to say they're protein strings here, meaning they come from the amino acid 20 symbol alphabet. But they could be any strings that we look at. And our output is going to be the minimum number of single element mutations to change string 1 into string 2. Those edit operations that we specify that we allow are substitutions, insertions, or deletions of a single symbol. to solve this problem, we're going to keep in mind that, well, this seems similar to what we've seen already with thinking about alignments and connecting them to paths in a network. So we will look then at our alignment of two strings that we had before and its connection to a network where alignments correspond to paths in the network. So in this case, you have two matches followed by this insertion of a C, followed by two matches, followed by this deletion of a T from the top string. And you can trace this by saying the diagonal edges are matches or mismatches. The insertions are horizontal edges, two more matches, a deletion, a mismatch of an A against a C, another deletion, and a mismatch of an A against a C. So we've got that correspondence between alignments and paths. But in this particular case, if I'm looking at the edit distance, what I want is, when I produce an alignment, I want to categorize over all these different possibilities. Matches are going to contribute a score of 0. All of the mismatches and indels, meaning insertions or deletions, they're going to contribute a cost of 1. And in this particular case, what I'm looking at is a path of minimum length from the top left to the bottom right. Now, if that's the path that I'm interested in, everything is going to be essentially the same, but I want to make sure that, well, I frame this problem as a minimum of 3 things when I'm at a current node. And I could really try to force this as a longest path problem if I said, well, the matches are going to get scores of 0, the insertions and deletions are going to get a -1, and the mismatches are going to get a -1 too. And so I'm finding the path from top left to bottom right having maximum score, and that maximum score, if that's -6, for example, what that means is the fewest number of edges that are not red from here to here that I can take on any path is equal to 6. And so my edit distance would be equal to the negative of -6 or 6. That's a nice idea because it allows us to kind of apply one framework of taking the longest path. It's also going to be a little bit annoying in terms of trying to understand what's going on. So it's probably a lot simpler to appreciate, well, I'm still going to have a recurrence relation, but the recurrence relation is going to be the minimum instead of taking a maximum. And what I'm thinking about is I'm looking for paths that go from here to here, and I'm trying to accumulate as few horizontal, vertical, and diagonal mismatch edges as I possibly can. If we look at our code for this, it's probably not surprising then that our starter code consists of 2 functions. The first one is going to say, let's make a table applying our recurrence relation. And the second one is going to say, what am I interested in terms of the edit distance? And the edit distance is really just going to be the bottom right element of that table. So the edit distance function is going to be an easy function to write, but it's nice that I separate this out as a separate function that says, take 2 strings, produce an integer corresponding to the minimum number of insertions, deletions, and substitutions needed to transform one string into the other. I'm going to assume that I've made my beautiful edit table for S and T, and then I want to take the bottom right element of it. So in this particular case, I'm going to return, what is it, row index equal to length of S, and column index equal to length of T. I know that that's the bottom right element because we always know that there's one additional row and column in the table. So we're going to have number of rows equal to the length of S plus 1, and the number of columns is equal to the length of T plus 1, meaning the final index is going to be length of S for the rows and length of T for the columns. And that function is written. So the only thing I have to do then is write the edit table function that's going to build in a big table that's going to store at a given point in time, the element ij is going to be the minimum number of insertions, deletions, and substitutions up to that point in time. And up to that point in time, meaning I'm going to take the substring of S that starts at position 0 and ends at position I, so it has length I, and the substring of T having length J, that's a prefix as well. So if I look at my network, for example, I'm going to eventually want to fill in this value of the table, and that value of the table is going to correspond to the best edit distance I can get, ending here, meaning aligning this string against this string, which are just the two prefixes that I'm interested in. Returning to the code, then, it's just a matter of doing the same sort of thing that we've done before. We want to know how many rows are there going to be? Well, it's length of S plus 1. How many columns are there going to be? Well, that's length of T plus 1. And then as we do this, I want to make a table, and that table is a list of lists of integers. So a two-dimensional list of integers, it's going to start off as empty. I want to range over the number of rows, and I want to make the current row and append it. So I'll say the current row is equal to a list of integers having one dimension, and it's going to be equal to a bunch of zeros. How many zeros, you say? Well, it's just the number of columns. So after I've done that, I'll say append this to the table that we're growing. At the end of this process, I eventually want to return DP, but this says just initialize the table to have 0 values. If we remember what happened when we initialized the table for longest common subsequence, the entire initial row and the entire initial column should have been 0 because I couldn't accumulate any matches along that initial row and initial column. If we think about our magic connection to an alignment network, that's not going to be the case for the edit distance, because as I move across the first row, I'm accumulating a lot of mutations. So if I were here, for example, I'm aligning ATC against nothing, which means I'm picking up 3 horizontal edges and I'm penalizing each of those with a 1. So I can set all the values of the initial row and the initial column, but I want to make sure that they're not 0. This should be 1, this should be 2, this should be 3, 4, 5, and 1, 2, 3, 4, 5. The good news there is there's an easy correspondence, which is I'm going to range over all of the rows, and I'm going to set everybody in the first column to be equal to whatever the row index is. Okay, so what we're doing here is range over the first row and column and set the element at index I equal to itself, equal to I. So this has ranged over all the rows. I'm also going to range over all of the columns, and I'm going to set dp of 0j. So this is in the 0th row. I'm going to set its value equal to j. Once I've set those values, now I've got the first row and column, and now I just need to range over the interior of the table and apply my recurrence. So we see the same structure here appearing that we had when we were looking at a longest common subsequence. And this is why this framework is so useful, because we can keep adding little additional modifications to sequence alignment to make it a little bit more complex. And at every point in time, it's just a matter of making sure that we figure out how our framework needs to adjust, which largely means how is it that our recurrence relation and our initial conditions, of course, need to change. To range over the interior of the table, I'll have a row index that ranges from 1 over the number of rows. I'll have a column index that ranges from 1 over the number of columns. And then when I'm at a current element, what I want to say is consult, 3 values. The up value is going to be looking at 1 row previous to me. So I'm looking up. So I'm going to say row -1 and call. And I'm going to add 1 to it because I need to make sure that I assess the penalty associated with saying this has to be a mutation. The left value, as we saw before, is what happens when I look 1 column previous. I'm going to add 1 to that value as well. And now the diagonal value is going to be, well, I know that I'm looking 1 previous row and 1 previous column index, but it's going to potentially vary. It could be that this needs to be a +0 if it's a match. It could be that this is a +1 if it's a mismatch. So I'm going to set it equal to just the value of the table. And then I'm going to make a check to see if it's a mismatch and add 1 if so. So is it the case? Unfortunately, we're not going to have to worry about figuring out the pattern again because this is a problem that we have already solved. We know how to consider if the current two symbols, to know what the indices of the current two symbols are. What I'm looking at is I'm looking at S of rho minus 1, and I'm looking at T of col minus 1. And I'm saying, is it the case that it's a mismatch? Okay. Are those two things not equal? And if they're not equal, then I want to add 1 to diag. That's one way of doing this. That would allow me to say, well, at the end of this process, I'm going to take dp of rho col, and I'm going to set it equal to not the max, but the minimum of up, left, and diag. The other way to do this would be to say, well, that might make sense to you. I like this probably a little better. We could also say, well, if you have a mismatch, then I want to add 1 to the diag value. And I'll take the minimum at this point in time. Else, I'm going to say there's a match. Okay. And if there's a match, then I'm going to still take the minimum of 3 things, but I'm not going to add 1. And that's because I didn't add 1 previously. Whichever of those two frameworks or formulations of this problem you prefer is fine by me. At the end of the day, we have solved the question, and so we can take a look at our sample by running this. We see we got a value of 5. Okay, that was what was expected. So let's get a larger data set. We're going to name it data set. We're going to comment out the parsing part of the code. And we're going to run it again and look at the output. So we get 377. I could just copy that in from the terminal, of course, or typed it. Let's be very fancy, 377. And a problem that seems like it was going to be pretty challenging to solve because of the framework of dynamic programming and the idea of finding a longest path in a network is actually quite short because it's just a matter of generalizing what we already know. If you have questions on that, let me know. We're going to look at EDTA next. All right. In EDTA, we're going to look at producing an edit distance alignment. What this means is that in a previous question, we have been able to determine the edit distance between two strings, meaning if I have two of these strings, what is the minimum number of single character substitutions, insertions, and deletions to change one string into another. But what we care about is making alignments of strings. And so our input here is going to be 2 strings. And the output is to produce the edit distance, I guess sort of as validation, which is something we already know how to do, followed by an alignment of the 2 strings. So you'll notice that we've added in gap symbols here into either of the 2 strings. That corresponds to the alignment that you would get corresponding to an alignment path in our network that only accumulates 4 total non-match edges. And you can see that here. So the matches are not going to contribute, but E against a gap is going to be 1. Y against an E is going to be another one. And then we have 2 more at the end of our alignment. So that's where we get the distance value of 4. The previous problem that we looked at computed the edit distance, so we know that this value would have to be 4. We know how to solve that. But what we haven't talked about is how to produce the alignment itself. Fortunately, we know that we have this correspondence between alignments and paths through the network. We've already produced a table that would, for a given position, say what is the minimum number of edit operations required to transform the string ending at this row into the column ending at the string ending at this column. And the edit distance is just the value in the bottom right, meaning what's the minimum number of edit operations required to transform string 1 into string 2. And now that we've got that point, or that problem solved, we're going to do the same thing that we did when we solved the longest common subsequence problem. We're going to backtrack from the bottom right to the top left and reproduce the correct alignment. So if this were the edit distance alignment of these 2 strings, then what we would need to do is start in the bottom right of our table and ask progressively as we go backward, which value did I come from? So when I computed this as a minimum of 3 things, which of the 3 possible values of the table corresponds to that minimum? So when we come back to our code, we have an edit alignment function that we want to write that takes 2 strings, and it's going to produce 3 things. So it's going to produce the edit distance itself, but then it's going to produce 2 strings corresponding to the first row and the second row of the alignment of the 2 strings that we have as input. So what we know we're going to need to do is to form my edit table of the 2 strings, which means I should import from the edit file the edit table function that we wrote. That allows me to call this function, and I've done half of the problem already. Because once I've formed that table, well, I know that at the very end of this, what I'm going to return is the edit distance, something, and something else. And that edit distance, after I've done this, is equal to the bottom right element. I could, of course, also call from the edit.py file, I could call the edit distance function. But in this particular case, I know what it is. It's just the bottom right element. So I don't really need to call that function. What I do need to do is produce the alignment. So this part of the function is finished. But I need to make sure that I produce the alignment itself. So here is where what I want to do is I want to range over the values of the table and build an alignment as we go. So in this case, let's say to go backward, we're going to apply the same approach that we had when we were finding the longest common subsequence. I'm going to set R as my row index that I'm going to use to say where am I. R is going to be equal to length of S. C is going to represent the column that I'm at, which is going to start off as the length of T. So I should say what we're doing, generate the table of values for the edit distance. and declare row and column indices corresponding to the starting point. Once I've done, that's probably too long of a comment in Python, but that's okay. Once I've done this, well, let's create our strings. So I could say I want a string and I want a string. We're essentially going to augment S&T, possibly by some gap symbols as we go, but this is going to be our first row, and T-aligned is going to be our second row. So we're going to declare 2 rows of the alignment. But there's one important consideration, which is that during this process, I don't want to just do a bunch of string concatenations. So what I'm going to do instead is declare a list of strings. It's going to start off as empty. And in the case of T-aligned, I'm going to declare a list of strings. It's going to start off as empty. And then at the end of this process, I want to return S-aligned as the second element of what happens in my return, and T-aligned as the third element, except I don't want to return a list of strings, I want to return the join of them. So we're going to use this trick that we've seen a million times, which is I'm going to join everything here, and I'm going to use an empty string.join and form a string out of the second row. So now we know what the return is going to look like, and it's just a matter of saying, I've got the bottom right element as the distance. I know what those 2 strings are going to be. I've declared my 2 rows, but we want to range over the values of the table and build out the 2 rows of the alignment. So let's range over the interior. We know how to do this. I'll say while it's the case that R is greater than 0 and C is greater than 0. This is going to be very similar to what we saw with forming a longest common subsequence. Let's look up first. So to do that, I'll say, is it the case that dp of RC, that's our table, is it equal to what happens when I look up, which is 1 row above me, and the same column? Is that equal to that value plus 1? Because this means I accumulated 1 mutation or 1 character change coming from above me. So when I computed the table value, did I have equality there? If we look at edit, remember when we made our table, you consult 3 values. The up value, the left value is the previous value plus 1. The up value is the previous value above me plus 1. And then the diagonal value might be a plus 1 if it's a mismatch, or we're at a match, in which case you have equality. So we just need to make sure that we say at a given point in time, where did I come from? If I came from the element above me, I'm looking up. And if I'm looking up, I'm saying, all right, great. We want to say, what is it that I'm actually building? Well, I want to build, add the appropriate elements to the alignment. And if we think about an up edge in our alignment, well, if I'm looking up, I'm going to take the current symbol from the first string, and I'm going to align it against a gap in the second string. So for that reason, S-aligned is going to get a symbol. So S-aligned dot append, we're going to say the current symbol of S, which is R minus 1. T-aligned, however, is going to say, I'm not going to say T of C minus 1, that's tempting. I'm instead going to say a gap symbol. Okay, so this is a vertical edge. And if it's a vertical edge, then at the end of this process, once I've added those to my alignment, then I want to R minus equal 1. I'm going to have an else if that says if dp of RC is equal to the left element plus 1. So the left element means 1 column to the left. If that's the case, then I want to say S-aligned dot append something, t aligned dot append something else, and c minus equal to 1. And if we look at our table and say, or our network, and say what happens when I have a left edge, I'm at this node, I'm looking left. That means that I'm taking a symbol from T, but I'm not taking a symbol from S. I'm instead going to have a gap symbol there. So I'm switching these two cases where S aligned is going to get a gap symbol, and T aligned is going to get the current symbol of T, which is T of C minus 1. And then I subtract a value from C. So I'm, in this particular case, this is my horizontal edge, and we're going to move left. Then I have other cases. A better way of doing this would be to say, let's, check the edit table values to make sure that they're valid. And we probably should discriminate between a match and a mismatch. But in terms of building the alignment, regardless of whether it's a match or a mismatch, if I'm looking up and to the left, I'm going to be taking the current symbol of S and the current symbol of T. It doesn't matter if it's a mismatch or a match here, or it's a mismatch here. In this case, I'm taking an A against a C, which you see over here. So because that's the case, well, I'm going to take both symbols at current position of S and T. So I'll take this element here, and I'll take this element here. I don't even need to retype them. And I know that I'm looking up and to the left, so I'm reducing R by 1, and I'm reducing C by 1. And I'm moving up and to the left. Now I've built out my alignments. Once I've done that, it seems like we're finished. And I'll show you what happens. Let's run this on our sample. So our sample is S and T. So I'll run Python 3 EDTA.py. And there's a couple of issues. So issue number 1 is, as we saw before with LCS, we've got a nice alignment here. That surely doesn't look like an alignment of pleasantly and meanly. And we don't have quite the same output here. I could do pretty and protein. But everything appears to be not quite right. Issue 1 is that as I've built my alignment, I'm building it correctly, I think. I hope. But I'm building it backward. So as I'm building this backward, what that means is once I get to, the end of my function, once I've made the alignments, I should reverse them. So both alignments are backward. So we reverse them. It would be better to just prepend these symbols that we see to the start of my list. Unfortunately, Python really likes it when you append things to the end, which kind of forces us to then have to then reverse these things at the end. But that's okay. That's not a big deal. S-aligned.reverse and T-aligned.reverse. So now I'm going to change just that, and now I get pleasantly and meanly. I could trick you by saying, this appears to align everything here. Let's see what happens if we say pretty and PRTTEIN. So that's the sample from online. And everything here looks okay too. So we get a value of 4, which is what we see there. We get a different alignment, but that's all right. No big deal, right? As long we know that could be multiple solutions here, depending on how we backtrack. Sometimes there's going to be a tie, so we can go up or left or whatever if there's a tie. There is an issue though, and I'm not going to get an incorrect solution. I'm going to tell you what it is. In both of these samples, and this is as we've seen a lot with how we think about how we solve problems on Rosalind. You get these small data sets and our code might be working, and then you get a larger data set and it doesn't work. So a better paradigm would be, let's come up with many, many small data sets. And all those data sets are going to test like one little thing. And that's why you should check out our bioinformatics algorithms project, where we have a print book, but we also have a full interactive text where you can implement all these algorithms and many other algorithms. And all of those coding challenges that we have to allow you to understand how all this, kind of connects together, they all are based on this idea of lots of little tests. And so the problem becomes, well, I don't know, what would happen if I had two strings that aren't actually very similar? That works, okay. I can't get this to work. I need to think creatively around what my test data set needs to be. I think our problem here, okay, let me switch them. Let's try this. So there's no matches there. Okay, that works too. Oh well, all right. So in each of these cases, what is happening is the very last thing that we've had, like if you look at our outputs, the very last thing that has happened is that we go diagonally. And this is actually nice because in all of these cases, so this actually would work. The reason why is when it goes back to a point that I made in a previous problem about bias. And by bias, I mean just something as simple as the order in which you perform these checks. So the order in which these checks happen is always going to try to go up and then left before it consults the diagonal value. So it's only going to make the diagonal value as like a last resort. And what that means is if you have to have diagonal edges, they're going to be saved for the very end because R and C are going to start off big and they're going to get smaller. So as a result of this, the alignments that we produced, and we can see it in either of these cases. So we can see it pleasantly and meanly. We did this way. We're kind of going to prefer getting our indels out of the way early. So you can see it here, for example. And we have the same thing happen here. So, but we're adding these gap symbols early on when we're forming the alignments. As a result, this will cause more diagonal edges to happen later, meaning more matches or mismatches later. There is a bug here, though, which is that it might be possible for you to backtrack and eventually hit, I don't know, you could hit this initial row or this initial column. And we are only ranging over the interior of the network. So in every case that we've seen, we've gotten to this node and we've gone here. So everything is fine. But if we have a test case, or we wrote our algorithm such that there's a test case where we eventually just hit, I don't know, this node, then the algorithm would just say, okay, I'm done. But the problem is that if we end here, we're going to be missing out. We've used all these symbols of S, but we've not actually used all the symbols of T. So our alignment would be a little bit short. And without rewriting the code, it's going to be hard for me to construct a test data set where that's going to be the case. It's better to just make sure that our function is technically correct. And so at this point in time, there's one tiny important issue, which is, well, we could technically be not at the origin if we are in the initial row or column. So we need to have one little extra check to say, is it the case that R is positive? So if R is positive, I'm in that initial row. And if R is positive, then I'm going to say, all right, well, move up to the top left. Okay. And so for as long as R is positive, I'm going to do the exact same thing that I did when I moved up. So when I move up, I do these three things. So I just take that code, copy it down, and say, let's do the same thing. I'm going to take the current symbol of S. I'm going to compare, I'll also take a gap symbol for the second row of the alignment corresponding to T. And then I'm going to move up one step. So this will just carry on adding the remaining elements to my alignment. I also could be in the first row. So if I'm in the first row, well, I want to check that says, while it's the case that C is still positive, I'm going to move left. So I'm going to take all the stuff that corresponds to moving left, and I'm going to move left. Right, so we do that. That's not going to change anything on my samples, but it's going to make for a correct algorithm. And now it's going to prepare us to comment out all of our parsing. Make sure that we get a data set from the Rosalind platform. Download it. Put it into our folder. Name it dataset.txt. Run again. It's very quick, showing the beauty of this algorithmic framework for solving problems. And our dynamic programming solution is giving us the correct answer. Maybe try this problem, if you like, without that additional bit of code to make sure that we handle what happens if we're in our initial row or our initial column. But for now, I think we can consider our work on this particular problem finished. We're going to look at one more problem today, which is SCSP. YP, I agree with you that it is awesome that all these problems can be solved with almost the same code. Very much so. Very much so. In fact, you could really just have it as one function, kind of, to make one table where you generalize this out further. So you say, what are the edge weights that correspond to like horizontal, vertical, diagonal? You know, what are those edge weights? In LCS, they're zeros and ones, where the match edges are 1. In the edit distance, they're, well, you're taking a minimum, but as I said, you could frame this problem as a maximum if you weight all of your mutation edges, so your vertical edges, your horizontal edges, and your mismatch edges that go diagonally. If you weight all those with -1, and then you weight the matches with 0, you actually could just specify those as inputs, like more parameters to your code. And then if you specify those as parameters to your code, one solution would give you the solution to both problems. The only thing that you would have to change is the parameters that you care about. That's what we're going to do in our next alignment code along, which is to say, actually, you know, this problem, or this problem I should say, and this problem are all basically solvable with one function. And that function is going to be much more general than any of them, because we're going to allow ourselves to not just charge matches 1 or mutations 1 and everything else 0. We're going to say, if you want to charge an indel equal to -47 and a mismatch equal to -12 and a match equal to 3, go for it. And then we can change those parameters however you want. You can solve a huge number of different potential applied problems just by taking this idea and extending it out to one more level of generality. But we're just not going to have time to do that today, and that's what we'll talk about next time. All right, SCSP is going to be the last problem we look at. Do you think maybe it's going to be the same thing? Like, could it be that actually we're going to use the same ideas? Nothing's really going to change that much, even though the problem's going to seem very different. All right, let's see. SCSP is interleaving two motifs. And we've worked up to this point in time with subsequences. So a collection of symbols that occurs inside of a longer string in order, but not necessarily contiguously. We're now going to view it in kind of the opposite direction, which is a supersequence of a string is a larger string that contains that string as a subsequence. So it might not surprise you that we are looking at this and probably thinking about something like longest common subsequence, even if the problem itself here is a little bit different. Our input is going to be two strings, S and T, and we're going to specify here that they're from the DNA alphabet, but they don't have to be. And what we want to return is a supersequence of both of these strings, so a longer string that contains each of the two input strings as a subsequence. As we've seen with a lot of alignment problems, there might be multiple solutions to this question. That's okay. All those solutions, however, should be invariant in the sense that they'll have the same length. So for this sample data set, if we find a different answer, it should have length 9. Our idea, if we look at the sample, is to realize that, well, there's kind of an alignment here. So I'm going to take my sample data set and I'm going to look at it over in my scsp.py file. And this is our input. And the output that I'm going to have is, in this case, ATG, CAT, GAT. So that's our input. Our output is ATG, CAT, GAT. And it might not be readily apparent. However, there's an alignment present of the input strings that would allow us to see this output very quickly. I'm going to show you what it is. So if I were to say AT-C-TGAT and -TGCA T-A-. So you might say, Philip, where on earth does this alignment come from? Well, if we were to form this alignment, I think you can see that it's the symbols of the first string in order, and it's the symbols of the second string in order, and we have some occasional gap symbols inserted in between them, and we never have a gap against a gap, so this is a valid alignment of the two strings. Let's look at the corresponding columns. So you have an A against a gap, and that produces an A. So in this particular case, well, you have to explain this A in the first string, but I don't have to explain that A in the second string. This match column corresponds to explaining this T. Again, you have an indel column, so we need to explain the G in this string. And so we can do that by looking here. Then we get another matched column, so we can explain this C in both of S and T, the input strings, with one symbol. The question is, what is this alignment? This alignment is as short as possible, in some sense, and has no mismatches allowed. The idea is, if there were a mismatch that were allowed, well, if I had a C against a T, I couldn't infer a symbol in my superstring from that position. It wouldn't make any sense. So I need to separate those out. And if that were the case, I could just separate them out as, instead of a C against a T, I could go C against a dash or dash against a T. So it's as short as possible and it has no mismatches allowed. Those two things kind of go hand in hand. So as short as possible means maximize the number of matches. And now we realize that this problem is a different problem in disguise. So this is LCS in disguise. And there's a key point, which is there's a formula even, which is that the length of the shortest common supersequence, I'm not going to type all that out, is equal to the length of S plus the length of T. But there are some positions where, so a position like this has to get used by S, a symbol of S. A position like this has to get used by a symbol of T. And it's not explainable within S. But what we're trying to do is we're trying to maximize the matches. So I can subtract from this the number of symbols that are common to both. And that's just an LCS of the two strings. So the length of a shortest common supersequence is the sum of the two strings' length, and then you subtract away any shared symbols that you were able to obtain. And those shared symbols are just the matches in the best possible alignment, meaning the alignment corresponding to a longest common subsequence. So again, math rears its head, but if we know a little bit of math, we can quickly obtain this formula. The only issue is we're not being asked for the length of a shortest common supersequence. If we were, that would be a cool problem, because then I could just say, what's the length of S? What's the length of T? Compute an LCS of S and T based off of what we've already done by solving the longest common subsequence problem. Take that LCS, determine its length, and subtract it, and your problem is solved. However, unfortunately, in this problem, we're looking for a string corresponding to the supersequence itself. So what we're going to need to do is we're going to need to build the alignment. And to build the alignment, we really only care about the alignment that corresponds to LCS, or I should say the table, scoring table that corresponds to LCS, which means that, I want to, from LCSQ, I want to import the function that we had, which was LCS score matrix. And that function that we wrote is this LCS score matrix function. So I've made sure I've imported that. That's going to it takes a list or a string. In this particular case, we can plug in a string to it, and it's going to give us the scoring table. So that could be pretty useful. And that's where this is going to start. So it's not going to surprise you that we're going to see the same sort of thing that we've seen before. Let's get the scoring table for LCS. So I'm going to call that DP. Okay. And so I've imported my function. I call it here. Then I'm going to set a row and column index that we're going to start with. R is equal to length of S. C is equal to length of T. And then we're going to declare a result, which is a list of strings equal to an empty list. Eventually, I'm going to return the join of that result. So I'm really building a string, but I'm establishing that as a list. So here we're going to establish the row and column index that I care about, plus declare our result list. Okay. And then we trace our way back. So while it's the case that R is not equal to 0, and while it's the case that C is not equal to 0, so we're going to start with the interior of the table. So while that's the case, I'm going to say I'm really looking for an LCS kind of. But as I'm looking for that LCS and I go backward, I also want a bigger alignment. So before, I'm only interested in T against T, C against C, T against T, and A against an A. This time, though, I actually want to build out the other possibilities. And the other possibilities here are, well, if every time I have a vertical edge or a horizontal edge, so every time I see a vertical or horizontal edge that I use as part of going backward, I actually want to remember those two. The only thing that I don't want to remember is the mismatch edges. Those are invalid. So what I will say is I simply will not allow them to be used. And what I will say in this particular case is, let's check. So is it the case that the two corresponding symbols are equal. I can't be quite as loose with this and say, oh, well, if I come from the diagonal edge, I know that I'm going to append both of these to my alignment, which is what we did when we formed the edit alignment, because I want to make sure that I'm actually checking that the symbols match. So I'm going to show you, here's a way of checking the diagonal edges first, and I only care about diagonal edges that correspond to matches. So if I have a match and the current element is equal to whatever the previous diagonal, meaning over one row, up one row and over one column, and then I check that as equal to +1, because then I know that I'm at a match. So this is a match, which is good, and add it to the alignment, meaning I don't even need to form the alignment. I'm thinking about this as an alignment problem, but the only thing that I want to form is the superstring. And what I want to form is add the current symbol to the superstring. So the current symbol is one of two things. I'll say the result.append. It could be s of r minus 1, or they're equal. It could be t of c minus 1. And once I've done that, I want to move diagonally. So I'll say r minus equal to 1 and c minus equal to 1. And once I've moved diagonally, I can say, good, I'm done. I just need to make the other checks. So else if dp of rc is equal to dp of r minus 1 and c, well, this is our case where I'm going to say I'm looking one row above me, and with the LCS score table, I don't have any edge weight associated with it. So I'm going to say r minus equal to 1. And that's because this is, move up. And when I say r minus equal to 1, if I'm moving up, well, that means that I have an indel in my alignment, and I want to add it to the string, because every time I see an A against a gap, or an A against a gap in this way, I want to make sure that I add the appropriate symbol from that string to the growing supersequence. So the first thing I want to do is result.append, and I've moved up in the rows, so I'm considering the string that's associated with indexing those rows, which is just s of r minus 1. So I'll append that value. And then I finally have a, an else. In this particular case, I'll say elif dp of rc is equal to dp of rc minus 1. And in this case, I'll say, move left. And to move left, I'm considering the current symbol of t. So I'll take t of c minus 1 and add it to the result. And then I'll subtract 1 from the column index. I was thinking of rearranging these. Okay. And I think there's probably an else here, which is just to continue. So there's a final consideration, which is, I have a mismatch. So meaning that s of r minus, or dp of rc is equal to dp of r minus 1 c minus 1, but I don't have this being equal. And in that particular case, I don't want to carry on. Then we want to actually make sure that what we also do is take the result and reverse it. And now when we can take a look at this, let's see what happens. So we've got our sample. We have ATCG, ATC-TGAT, and TGC-ATA, and we're expecting something of length 9. So when we Python 3 and run SCSP.py, we do not obtain anything of length 9. We obtain it of length 8. And so from when we solved the edit alignment problem, EDTA, we saw that it's really important to make sure that at the end of this process, you don't end in the initial row or the initial column. That would be bad. And so you see, we've almost got it right, but we're missing one symbol off the start. And the reason why is, if you look at our alignment that I produced for this very data set, the last thing that you want to do at the very end of this is you want to take a symbol from the first string, but not the second, meaning I want to move up. And what we're currently having happen is, when we backtrack through our table, we're ending here. But we actually want to make sure that we go back to 0, 0, because we've left off a symbol, which is this A against a gap. And so in this particular case, we're kind of stuck at that node. And we didn't actually see this as a bug when we worked with the edit distance alignment, because we were just lucky with all of our tests and the way that in which we had written the code. We were lucky that we were always ending with a diagonal edge. But if you don't end with a diagonal edge, you're going to be stuck here. And fortunately, this is very fixable, because we're going to have, as long as I make sure my indentation is right, we're going to have a while r is not equal to 0, we're going to do something. And while c is not equal to 0, we're going to do something else. And we're going to do the same thing that we did in the edit alignment, which is, while the row value is non-zero, I know I'm in the first column, so move up. And while c is not equal to 0, I know I'm in the first row, so move left. And I'm just going to do the exact same thing that I do in each of these. Here's the benefit of having comments, because I can just see, oh, move up, I know what I do there. I'm going to append the current symbol of S, and then subtract 1 from R. And when I move left, I'm going to append the current symbol of T, and subtract 1 from C. And now, when I update this, and I run my code again, I get the correct answer, which has length 9. And I can be confident, hopefully, that I can comment out my parsing code. I can expand out my file explorer. I'll grab a data set from Rosalind. And I'm going to call that dataset.txt. And run it again. We get something in output. And I hope it's right. I hope. And we win. Okay. So what's also nice about all these functions is that they're also pretty efficient. We're able to do something that by hand would take us a really long time to make this huge table of the number of rows is equal to the length of the first string plus 1, the number of columns is equal to the length of the second string plus 1. We'd have to go through and fill in all the values. Then once we finally filled in all the values, we would have to trace backward and form our alignment. Even though Python is, in certain contexts, a very slow language, it still produces a result for these data sets very rapidly. In, I think, this case, it was about a second. So to conclude, we've seen how dynamic programming really helps us solve problems in alignment. And we've noticed that the structure of our code is very similar for a lot of different problems around alignment. There is a larger lesson to be learned, which is that a lot of times when you start writing code that's very similar, or you have code that's similar in solving a bunch of problems, there's a good chance that there's probably just one function that you could have written that would have solved all of those problems at once. That's the kind of thing we're going to do when we generalize our work with alignment, and we work with what's called global sequence alignment, where I'm going to extend this to say, instead of having hard-coded parameters for what the weights of our edges are in my alignment network, I'm actually going to allow myself to have parameters that could vary according to different possible penalties and different possible rewards. So there are a lot more problems in alignment to solve. Even when I solve that generalized version of the problem, there's going to be additional extensions of this because biologists want to make sure that the alignments that we produce are accurate. And it turns out we need a lot more biological knowledge to attain that accuracy, which means we're going to need to power up our algorithms in return. But we're also going to use dynamic programming in contexts as we go through the platform that are not necessarily only related to sequence alignment. We're going to start seeing problems in counting things and other computational biology applications, but also some applications that are just really like fun exercises involving dynamic programming that turn a problem from something that seems like it would be very challenging to solve to something that an algorithm is going to solve in a second for us. We're going to see more about both of those types of applications, dynamic programming outside and inside of sequence alignment, in a later stream. So I'll plan on seeing you then. And until next time.